Okay, you guys, let's find the Taylor series for f of x equals natural log of x when a equals 2. So the Taylor series centered at 2. Let's do a little bit of review here. F of x equals, assuming it has a Taylor series, what is it? It's good to start out with the sum. N equals 0 to infinity. So what does that mean? Nth derivative evaluated at a, yeah, over n factorial times
x minus a quantity n
to the n, yeah. And so if you just memorize this, you can get what it looks like when you multiply, or when you write it out, rather, longhand. So what does this look like when you write it out longhand? What's the first term? F of a. Remember, the agreement is when this is not an exponent, it's the derivative, this n up here. The agreement is when it's 0, that's just f evaluated at a, right? That's the function. The 0th derivative is the function itself. That's the first term plus, what's the next term? The first derivative, right? N is 1 in the second term because we started at n equals 0. So first derivative evaluated at a over, well, 1 factorial, that's kind of boring, times x minus a to the 1 power, right? And then plus, what's the next one? F double prime a over, let's say 2 factorial just to kind of establish the pattern, times what? X minus a squared. And then you got it, I think. Once you do that term, I think you got the pattern, right? Now we want to find a Taylor series for f of x equals the natural log of x when a equals 2. So what does this formula tell you to do? You don't need to write down step 1, step 2, step 3. The formula tells you what to do. It tells you to find what? Well, ideally, you find this formula, right? Well, I mean, not even that. Really, the nth derivative evaluated at a, right? And then you plug into the formula for the sum, right? So that what? Okay, so you need the nth derivative evaluated at a, which means you need to start doing what? Taking derivatives, look for a pattern. Yeah, that's the key. So let's do it. Let me write down f of x. F of x is just the natural log of x. So that's f(0)x, right? The 0th derivative. Okay, f prime of x, what's that? 1 over x, which is x to the negative 1, right? F double prime of x. Well, it's going to be negative, right? Negative x to the negative 2 would be a good way to write it, I suppose. You could write it as negative 1 over x squared, right? That would work too. Okay, but to save room, I'm going to leave it as negative x to the negative 2. F triple prime. So it will be 2, positive 2x to the negative 3. F fourple prime. Fourple is not an official word. Okay. Okay, let's not do that. Let's look for a pattern. So let's not actually do the multiplication. Let's write the multiplication down. Negative 3 times 2 times x to the negative 4. F, what would be a good name for the fifth derivative? F fifth pole? Okay, would it be positive or negative? Positive. So positive 4 times 3 times 2, I'm sensing a pattern. Times 1, but we don't need to write that, I guess. X to the negative 5. I think that's probably enough for a pattern. Now, really what I want to do is evaluate these derivatives where? At what we're calling a equals 2, but a is an x value. So essentially x equals 2, right? So you could make a little, if you want, you could make a little table like this. So this is the, on the left side of the table, this is the nth derivative evaluated at x, so not really evaluated. And of course, if you wanted to put in another column, n is, well, I don't want to put in all those lines, but I'll just leave it like that. N is 0, 1, 2, 3, 4, 5, and then we want the nth derivative evaluated at a, right? Okay, well, how about for the function itself, f of a is just, well, a, let me be clear, a is 2, so I could actually write 2 right there instead of a. So f of 2 is just natural log of 2, isn't it? Yep. Okay, what do we get for f prime of 2? Yeah, we could write it as 1 over 2. 1/2. Okay, what do we get for f double prime evaluated at 2? Negative 1 over, let's write 2 squared. I mean, it's true. You're not wrong. It is negative 1 over 4. Okay, well, how would you write the next one? But I think it's 2, though, right? So I don't have a problem with what you said. I'm just going to write it as 2 in front. You were talking about x to the negative 3. It could be written as when x is 2, with that 2 cubed in the denominator, right? And then what? Negative 3 times 2 divided by 2 to the 4th for n equals 4. For n equals 5, 4 times 3 times 2 divided by 2 to the 5th. So what's, okay, let's do one more. What's the pattern then? Okay, dot, 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 for just n. And I'm not even worried about the nth derivative evaluated at x. I want the nth derivative evaluated at 2. What? Okay, first of all, does it alternate? Okay, disregarding this first guy. This first guy is an anomaly. An anomaly. Can't talk today. Natural log of 2. That doesn't fit any pattern, does it? But that's okay. We can separate that from the sum. After that, starting from 1 onward, what's the pattern? What's the formula for the nth derivative evaluated at 2? First of all, it alternates, so how am I going to indicate that? Well, the first one, that would be good, but we're looking at starting at 1, and if you plug 1 in there, then you get negative, but this is positive. Or plus 1, right? Either one, minus 1, plus 1 will work. I think in the notes I posted, I put plus 1. Doesn't matter. So that'll get me a positive first term. And then okay, on top, it looks like on bottom we're going to have a power of 2. Let's do that first. So 2 to the what? Yeah, notice this exponent matches n perfectly. This exponent down here, 2 to the power matches the n. So it would be 2 to the n. Whoops. Everybody agree there? And then what's the other factor up top going to be? Yeah, so 4 times 3 times 2, well, times 1 if you want to put it in there. Well, okay, this number in front then, disregarding the negative, is the n minus 1, isn't it? Yeah. So n minus 1 and then factorial. So that is just the nth derivative of f evaluated at 2, just part of the formula for the Taylor series, but it's the hardest part to find. Does everybody see how we did that? We're not done, obviously, but yeah.
So could we make x equal 2?
Well, that's a, yeah. A is a particular x value.
So we always do that for that right side of the table?
Yeah, yeah, because you're looking for the nth derivative evaluated at a. And a is a particular value of x, which is 2 in this case. In other cases, it's some other particular value of x. Yeah, they're a little bit confusing, but a always stands for that the value, the center of the series, essentially. Yeah. When we say a Taylor series centered at a, we're talking about that a is a particular value of x. Yeah. Okay, so then remember what we're doing. We want to go ahead and write out the series based on this formula. So we have to plug in this thing correctly. In fact, just so you can really see what's happening, let me rewrite it. So the generic Taylor series, f of x, and we're going to have to separate the first term, but the generic one has it starting at 0. The sum starting at 0, going to infinity. And then the nth derivative evaluated at a over n factorial times x minus a to the n. So that's what we want to fill in. However, that first term where n equals 0 doesn't fit the pattern. But that's OK. You can just separate it and start the sum at n equals 1. So we're going to write our f of x, our natural log of x, as, OK, the first term in the series. Oh, yeah, just to emphasize that, you know what I could do? I could say, oh, well, what do we get when we plug in n equals 0? Well, normally it's f of a, right? And then it becomes the sum from n equals 1 to infinity, the nth derivative evaluated at a, by n factorial, x minus a to the n. So in this particular case, I have to separate out that first term. But then the rest of them I can write using the series notation, which is always desirable. Well, almost always. OK, so what was that first term? What was f of a? F of 2 in this case. So in this case, again, a is 2. That's the natural log of 2, isn't it? Well, that's all we need, just natural log of 2 out in front. So, OK, natural log of 2 plus the sum from n equals 1 to infinity. OK, what did we get for this guy right here? Well, it's right above it, right? It's this guy right here, right there. So it'd be negative 1 to the n minus 1, and it's going to simplify, by the way, n minus 1 factorial. Now, 2 to the n, but what else belongs in the denominator? Yeah, I mean, if you, I don't want to show, I'll show it and then I'll erase it. If you look at the general formula, we're dividing the nth derivative evaluated at a by n factorial, right? Which would mean you divide this whole thing by n factorial. But that's, if you think of it as n factorial over 1, you flip and multiply, you get that factor of n factorial down here and erase the rest of that stuff, right? So let me clean that up. So long story short, in this particular problem, we get in the denominator 2 to the n times n factorial, and of course that's going to simplify, times x minus a to the, which is, well, what's a? 2 to the n power. Not done, got to simplify, but that's it. It's not wrong, it's just not simplified. Does that make sense to you? Then what did I mean by saying this simplifies? What do you see that simplifies? Yeah, this is n factorial, this is n minus 1 factorial. N factorial includes n minus 1 factorial, doesn't it? So if you just delete the n minus 1 factorial and the terms that come after n in the, if you write out n factorial long n, it goes n times n minus 1 factorial, so delete the n minus 1 factorials. In other words, divide them out. And we end up with a fairly tidy formula for natural log of x. Natural log of 2 plus the sum n equals 1 to infinity. What is it? Negative 1 to the n minus 1 or n plus 1. I guess I could write it as x minus 2 to the n power, all in the numerator, right? And then divided by 2 to the n. 2 to the n times n, yeah. Sorry, forgot the n. Now it makes sense. How would you find the radius of convergence? Or the interval of convergence? You would apply the ratio test to that sum, wouldn't you? Now, you've already seen lots of examples like that from 11.8, so I'm not going to show you it here. I'm just going to tell you what you'd do. You would apply the ratio, apply the ratio test to find I, the interval of convergence. I will just tell you that R, the radius of convergence, is 2.